Roger and I are going to tell you about some proposed new primitive functions, operators for Dyalog. I have a very small slot. This is yet again an attempt at a merge operator. It appeared in the conference in 2012 called merge, and last year it was called fusion. This year it's been reinvented and called at. So this is the at operator. And this is a live demonstration. This is a pre-release of 2016. It's just dumping in a session. So what at, if you look at a traditional modified assignment, what's happening here is we're assigning a name to the numbers from 1 to 5. We're using index origin 1 in this. Then reassigning the second and fourth item by multiplying them by 10 and then displaying the result. So this is old, 50-year-old APL to do this. Sorry? Oh, not modified assignment. Okay, well, 33-year-old APL. This is the equivalent, and you can see there's just at is a, oh, I got this. At is a dyadic operator. It takes a left operand and a right operand, and you can see the mapping. The 2-4 here goes to 2-4. The multiplication goes here. So the way we read this is the 10 times at 2-4 in iota 5. So it's just a rephrasing of this. And so what I'll be talking about, at has a left operand and a right operand. The left operand is a modifier, and the right operand is the selector. So at is a dyadic function. And here we can see there's a 10 and 100. It distributes in the normal way, as if we'd done a modified assignment with a 10 and 100 to the right. Let's move this up a little bit. Here's another example of a dyadic function. If we use the left tack, then this is equivalent to a non-modified assignment. It's just an assignment. We're putting 10 and 100 at those positions in iota 5. And we can use a monadic function. So this is reversing those positions. Roy? I'll repeat the question.
If the iota 5 is a variable, let us say it's a gigabyte variable.
Yeah.
This is suggesting that you make a copy.
No, I'll come to that. I'll come to that in a moment. Okay. The question is if the iota 5 was iota a lot, am I making a copy? Is this forcing me to make a copy of that? And I'll come to that in a moment. Okay. If the left operand is an array as opposed to a function, then that array is used as a modifier. So in this case, this is a replacement with a 2-item vector. So the left operand can be either an array or a function, and the right operand can be an array or a function. So this is nearly a shortcut for this version. There are some subtle differences. Right, the right operand is a selector. So here we have a selector as an array. Or the right operand can be a function. And this function is a member is a vowel, member jot, this. So if the right operand is a function, it returns a Boolean mask, which is used as a selection. And here is, now, so we have 4 cases. If you look up, the left and right operands can be function array, array array, array function, or function function, and they're independent. So what this is saying is the selector, is it a vowel? If so, apply this lowercase function to it. Oh, that's handy, isn't it? This is just a standard defun. So this is the lowercaseification of the vowels in the letters of the alphabet. You have a question, Mr. Kronberg?
Is L case called once or 21 times?
That's a good question. It is called once, and in fact, let me take a risk and use, there's a trace operator. I can trace the calling of that, and here we can see a trace is it takes L case takes this string and returns this string, and then that is implanted in the result. Okay, so these four cases are all right. The left, the modifier is either an array or a dyadic function, and the right operand is either an array of indices or a Boolean mask producing function. For higher rank arrays, so here's the traditional way of replacing alternate rows with 2x5 letters of the alphabet. This is how we do it with this. And for simple arrays, we select major cells. For vectors, it doesn't make any difference. I can use rank if I want to select columns. And there's an immediate difference between this operator syntax and modify and indexed assignment, is it's applicable under operators. This is reversing alternate rows to give me a zigzag. Yes. There is the tag. The tag there avoids the binding of the operand array with the argument array. Parentheses could do as well. Yeah. So a Dyalog has simple indexing, reach indexing, and choose indexing, and these are all available. So this is taking, this is putting stars at 1, 1, 2, 2, and 3, 3. And here's reach indexing is applicable, but there's no extra complication here. These are just available. Of course, being an operator, then we can apply. Doing modified assignment, we can't apply that under power very easily, for example. But here's do tenfold to the power 2. Do it twofold as an example. And of course, it has an easy inverse, so we could do tenfold to the negative power, which is an inverse of tenfold, a tenth. But these are not perhaps very useful example, but it shows the generality of bringing this operation back into the normal expression syntax. With a function, we have scatter point indexing. So if we're using a Boolean function, then this is tenfold alternate items. PCO is Roger's prime number function. 0 PCO says this is non-prime. So if I look at the non-primes in here, this is putting stars in all of the non-prime numbers in that array. Yeah, and it can be any rank array. Of course, it's not restricted to... Okay, so just to wrap up, the summary is you can emulate this using... this is a tool of thought wrapper on modified and indexed assignment. So if you're a denotative programmer, and denotative programmers are people who pronounce the left arrow as denotes, in the defuns workspace, which has, a couple of hundred functions, the only non-functional aspects now are indexed assignment, modified indexed assignment. So these would be, examples of those. Generally shorter expressions, we avoid the need to name the subject of a modification. It can be embedded in sub-expressions. It's applicable by operators, we've said this. There are some implementation challenges, and this is what Roy has pointed out. In this case, because v plus 3 has a ref count of 1, we can overwrite the second item. If the argument is the result of an expression, it has a low ref count, and we don't need to make a copy. In this case, we do need to make a copy because u and v are distinct arrays, so they can't have the same value. This is the challenge. This, at the moment, we can't overwrite v, and this would force a copy until we figure out a way of avoiding that using compiler techniques. We can overwrite omega if its ref count is 2 in this case. Can't easily overwrite omega. If you Google Dyalog item substitution, you'll see a model for this, and with lots more examples. Oh, sorry, this was okay, that's all I want to say. And I'll pass over to Roger now.
So I'm going to talk about 3 other proposed primitives. First one is where. So where, as Jay mentioned this morning, it's a replacement for the idiom. So where of a Boolean vector would give you the indices of where the ones are, and it would be qual-io dependent. And if the argument is a Boolean array, higher rank array, then it gives you the enclosed indices. So that's good for the scatter point indexing and replacement that John was talking about just a few minutes ago. And currently, where on a non-Boolean array is a domain error, but we can readily extend it in the future. It'll run at the same speed as the idiom, but it would replace a longish expression. And I claim that it's a qualitative difference because, well, I don't know about your brain, but my brain has limited cache space, and there's a big difference between one character and 1, 2, 3, 4, 5, 6, 7 characters. Okay, so it's the justification for it is a two of thought argument. The next one, it also uses the symbol iota underbar. It's IntervalIndex. If it's worth anything, it's already a primitive in J, has been a primitive in J for years. But what it is that it's a dyadic function, and the left argument, when and if sorted, divides the universe into, or not divides, but in particular partitions the universe into contiguous disjoint intervals. And it finds for each item, in fact each major cell of the right argument, the index of the interval which contains it. Okay, so if the right argument item is smaller than the first interval endpoint, then the index is 0 in origin 1, and -1 if it's origin 0, and so on. So the notation, okay. Which button controls the top? Okay. Right, thank you. The notation here is from conventional mathematics. The square bracket means it's equal to the endpoint, and the parentheses means it excludes the endpoint. So the first interval, the interval corresponding to the first interval endpoint includes the first endpoint and excludes the second one, and so on. And then the last interval endpoint is assumed to be infinity. And before the first actual interval endpoint in your data, in this case -1, there's an imaginary negative infinity as an endpoint. Okay? Brian.
How does quad I/O impact this?
Quad I/O would only affect the interval index. So if these interval indices are for origin 1, so it'll go from 0, 1, 2, 3, and so on, up to 5,
Right.
where 0 is when you're smaller than the first interval endpoint.
Right. So if you were in quad I/O 0,
Yeah,
what would -5 be?
it's not -5, it would be,
No, the last element of y.
okay, it will be -1,
Okay.
yes. Yeah, the suggestion is instead of interval index, we use interval index of as the name of the primitive. But yeah, I like interval index. Yeah, among other things, it's shorter. So it'll work on other data as well. In this case, character matrices. So x interval index of y. That's why it's better not to call it interval index of. Otherwise, I would be saying x interval index of y. Yeah? So these are the interval indices of y in x, where if you sort x, it divides the universe into, again, contiguous disjoint intervals. And then, so for example, JD all caps would be in this interval, because phi is the first interval endpoint. And JD with a lowercase d is in this interval. And if you're questioning the placement of these two, don't blame me, because that's the way gray up is defined. That's the collating sequence that I'm given. So as far as the collating sequence that's in the system, JD follows J. And then Jeff is between phi and J, right? Is it in this interval? And Anna is before phi, before the first interval endpoint, so it's here. Scott is after Roger. And Seuss is also after Roger. Yeah, the results of interval index are what they call in this country bee's knees as left argument for key, because you can use it. It's very suitable for use as a key to classify other data. So, for example, if I have an array T of timestamps, and X are the corresponding data. So, for example, these are the first and last 6 timestamps for a single day. And then I have a universe of timestamps for 5-minute intervals. Okay? Then this expression, I use U iota n bar, or interval index of T, gets a bunch of interval indices. Now, since T corresponds to X, these would be interval indices corresponding to X. And if I specify sum as the function for key, this expression would compute a summary of x in 5-minute intervals. It's not only succinct, but I think it's a superior for tour of thought, because I look at this and this is, okay, that's a summary of x in 5-minute intervals. It's not, you don't get lost in a computation on the timestamps to compute the interval index. I mean, you can, yeah, you can, yeah. Now you can do u under iota under bar t to get the interval index, and then other related computations can be had by using a different function operand to the key operator. Okay. I forgot a point in this. Yeah. If the in interval index, if the right argument, if all the cells of the right argument are in the left argument, you get the same result as iota, other than quad CT. So interval index is not quad CT dependent because it's dependent on gray, right? So I'm almost claiming that iota under bar is a better version of iota. Yeah. So the next new primitive, the final one that I'm going to talk about, is the tile dyadic operator. In the literature, it's sometimes known as the cut, tessellation, and stencil. I think in the conventional IT world, it's called stencil or stencil. Yes. It takes a function left operand and an array right operand, which in the simplest case is a vector. So this specifies the size of the tile in each dimension, and it's independent for each dimension. So in the first dimension, or the first axis, the size is 3. So it's 3 rows for each tile. And the 5 indicates that in the second dimension or second axis, it's 5 columns. So the sizes apply independently to each axis, and each element in the function argument, the right argument, has a chance to be the middle of a tile. Whoops, what happened? Oh, yeah, so each, so this is like a 4-5 reshape of iota 20, so it's going to 1, 2, 3, 4, 5. Can you see that it's in red, the middle of each tile? Yeah, okay. So so as the example illustrates, when you apply the operand function, it sees the same size argument. So it's always 3 by 5 that the operand function sees. I also want to say that this strongly resembles the tessellation operator that was presented last year. One difference between this and the tessellate is that the shards are the same, symmetrical. Right. So these zeros are not part of the data, but it's symmetrical on the left and the right, and symmetrical on the top and the bottom. Yeah. And another difference between this and the tessellate operator is that the operand function is given a left argument, which indicates how many, what's the size of the shard. So it can, if it wants to, know that it's being given a shard. So this is partly to answer Brian's question, is what happens when the argument has an even number of cells. It has no middle. So if it's even, we assume that the middle element has two things. So, for example, no. If the window size is even, right, then it has no middle, not the argument. So if the window size is 4, I'm going to say that it has two middle elements. So in that case, every pair has the chance to be the middle, okay, in red here. And if the window size is 6, or now the 6, then again the middle has two elements. Okay. Actually, an even window size is tricky anyway, because there are no middles. Yeah.
My definition, however, is very easy.
It could be that. It could be it's easy because it has no applications. I mean, really, because you want the shards to have some relationship to the original data, and you want as much of the original data as possible in your shard, which means it's in the middle. At least the middle is part of the original data. Yeah. Okay, I have 0 minutes left. Grab me if you have further questions, suggestions, so forth. Thank you. Oh, sorry.